Good morning. Our topic is waiting line models. Waiting in lines is part of everyday life. Some of us spend billions of hours per year waiting in lines, whether it is waiting in line at a grocery store to buy daily items or checking out at the cash registers, waiting in line at the bank for a teller, or waiting at an amusement park to go on the newest ride. We spend a lot of time waiting. We wait in lines at the movies, campus dining rooms, or at the registrar's office for class registration. Think about the lines you have waited in just during the past week. How long you wait in line depends on a number of factors. Your wait is a result of the number of people served before you, the number of servers working, and the amount of time it takes to serve each individual customer. Wait time is affected by the design of the waiting line system. A waiting line system or queuing system is defined by two elements: the population source of its customers and the process or service system itself. In this, we will examine the elements of the waiting line systems and appropriate performance measures. Performance characteristics are calculated for different waiting line systems. We conclude with descriptions of managerial decisions related to waiting line system design and performance. Here are some of the common queuing situations. This figure shows the waiting cost and service level trade-off. Anytime there is more customer demand for a service than can be provided, a waiting line occurs. Customers can either be humans or inanimate objects. Examples of objects that must wait in lines include a machine waiting for repair, a customer order waiting to be processed, sub-assemblies in a manufacturing plant, electronic messages on the internet, and ships or rail cars waiting for unloading. In a waiting line system, managers must decide what level of service to offer. A low level of service may be inexpensive, at least in the short run, but may incur high costs of customer dissatisfaction, such as lost future business and actual processing costs of complaints. A high level of service will cost more to provide and will result in lower dissatisfaction costs. Because of this trade-off, management must consider what is the optimal level of service to provide. Fast food restaurants illustrate the transient nature of waiting line systems. Waiting lines occur at a fast food restaurant drive-thru during peak meal times each day. There is a temporary surge in demand that cannot be quickly handled with the available capacity. In an effort to speed up delivery, some restaurants use an extra window: the first window for paying and the second window for picking up the food. At other times of the day, the restaurant uses a single window and may have no waiting line at the drive-thru window. The challenge is designing service systems with adequate but not excessive amounts of capacity. A fast food restaurant experiences variable demand and variable service times. The restaurant cannot be sure of how much customer demand there will be, and it does not know exactly what each customer will order. Each order can be unique and require a different service time. It is important to understand the different elements of a waiting line system. These elements include the customer population source, the service system, the arrival and service patterns, and the priorities used for controlling the line. Let us first look at the primary input into the waiting line system: the customers. The customer population can be considered to be finite or infinite. When potential new customers for the waiting line system are affected by the number of customers already in the system, the customer population is finite. For example, if you are in a class with 9 other students, the total customer population for meeting with a professor during office hours is 10 students. As the number of students waiting to meet with a professor increases, the population of possible new customers decreases. There is a finite limit as to how large the waiting line can ever be. When the number of customers waiting in line does not significantly affect the rate at which the population generates new customers, the customer population is considered infinite. For example, if you are taking a class with 500 other students, that's a relatively large population, and the probability of all the students trying to meet with the professor at the same time is very low, then the number of students in line does not significantly affect the population's ability to generate new customers. In addition to waiting, a customer has other possible actions. For example, a customer may balk, renege, or jockey. Balking occurs when the customer decides not to enter the waiting line. For example, you see that there are already 12 students waiting to meet with your professor, so you choose to come back later. Reneging occurs when the customer enters the waiting line but leaves before being serviced. For example, you can enter the line waiting to meet with your professor, but after waiting 15 minutes and seeing little progress, you decide to leave. Jockeying occurs when a customer changes from one line to another, hoping to reduce the waiting time. A good example of this is picking a line at a grocery store and changing to another line in the hope of being served quicker. The models used in this assume that customers are patient, they do not balk, renege, or jockey, and the customers come from an infinite population. The mathematical formulas become more complex for systems in which customer population must be considered finite and when customers balk, renege, or jockey. The service system. It is characterized by the number of waiting lines, the number of servers, the arrangement of servers, the arrival and service patterns, and the service priority rules. The number of waiting lines. Waiting line systems can have a single or multiple lines. Banks often have a single line for customers. Customers wait in line until a teller is free and then proceed to that teller's position. Other examples of single-line systems include airline counters, rental car counters, restaurants, amusement park attractions, and call centers. The advantage of using a single line when multiple servers are available is the customer's perception of fairness in terms of equitable weights. That is, the customer is not penalized by picking the slow line, but is served in the true first come, first served fashion. The single line approach eliminates jockeying behavior. Finally, a single line multiple service system has better performance in terms of waiting times than the same system with a line for each server. The multiple line configuration is appropriate when specialized servers are used or when space considerations make a single line inconvenient. For example, in a grocery store, some registers are express lanes for customers with a small number of items. Using express lines reduces the waiting time for customers making smaller purchases. The number of servers. System serving capacity is a function of the number of service facilities and server proficiency. In waiting line systems, the terms server and channel are used interchangeably. It is assumed that a service or server or channel can serve one customer at a time. Waiting line systems are either single server or multi-server. Single server examples include small retail stores with a single checkout counter, a theater with a single person selling tickets and controlling admission into the show, or a ballroom with a single person controlling admission. Multi-server systems have parallel service providers offering the same service. Multi-server examples include grocery stores with multiple cashiers, drive-through banks with multiple drive-through windows, and gas stations with multiple gas pumps. For the arrangement of servers, services require a single activity or a series of activities and are identified by the term phase. In a single-phase system, the service is completed all at once, with or such as with a bank transaction or a grocery store checkout. In a multi-phase system, the service is completed with a series of steps, such as at a fast food restaurant with ordering, pay, and pick up windows, or in many manufacturing processes. In addition, some waiting line systems have a finite size of the waiting line. Sometimes this happens in multi-phase systems. For example, perhaps only two cars can physically fit between the ordering and pay window of a fast food drive-thru. Finite size limitations can also occur in single-phase systems and can be associated either with a physical system. For example, a call center has only a finite number of incoming phone lines, or with customer behavior. If a customer arrives when a certain number of people are already waiting, the customer chooses not to join the line. For arrival and service patterns, waiting line models require an arrival rate and a service rate. The arrival rate specifies the average number of customers per time period. For example, a system may have 10 customers arrive on average each hour. The service rate specifies the average number of customers that can be serviced during a time period. The service rate is the capacity of the service system. If the number of customers you can serve per time period is less than the average number of customers arriving, the waiting line grows infinitely. You can never catch up with the demand. It is the variability in arrival and service patterns that causes waiting lines. Lines form when several customers request service at approximately the same time. This surge of customers temporarily overloads the service system, and a line develops. Waiting line models that assess the performance of service systems usually assume that customers arrive according to a Poisson probability distribution, and service times are described by an exponential distribution. The Poisson distribution specifies the probability that a certain number of customers will arrive in a given time period, such as per hour. The exponential distribution describes the service times as the probability that a particular service time will be less than or equal to a given amount of time. For the waiting line priority rules, or the service priority rules, a waiting line priority rule determines which customer is served next. A frequently used priority rule is first come, first served. This priority rule selects customers based on who has been waiting the longest in line. Generally, customers consider first come, first served to be the fairest method for determining priority. However, it is not the only priority rule used. Other rules include best customers first, highest profit customer first, quickest service requirement first, largest service requirement first, emergencies first, and so on. Although each priority rule has merit, it is important to use the priority rule that best supports the overall organizational strategy. For example, a first come first served rule does not make sense in a hospital emergency room and in fact could cause unnecessary deaths. The priority rule used affects the performance of the waiting line system. As an example, first come first served is generally considered fair, yet it is biased against customers requiring short service times. When checking out at a store that is using first come first served as a priority rule, a customer waiting behind another customer with a large number of items waits longer than a customer waiting behind a second customer with only a few items. Although processing is sequential, the wait times vary because of the preceding customer. Also, priority rules besides first come, first served may imply that some customers wait extremely long periods of time. For example, in a busy emergency room, someone at critically sick or injured could wait a significant period of time. The models that we are going to discuss assume a service system with a single waiting line, single or multiple servers, a single phase, and first come, first serve priority rule. Then again, for the characteristics of waiting line systems, we need to look into the arrivals or inputs into the system, the queue discipline or the waiting line itself, and the service facility. And this is an example of the waiting line. We have here the parts of a waiting line. We have there the arrival of the dirty cars to the system. Okay? And then arrivals from the general population, the queue or the waiting line, then the service facility, and then exit the system. From the population of dirty cars, okay, that is arrival to the system, and we need to look into the arrival characteristics. In the system, we have there the queue or the waiting line, and then, of course, the service facility. And then, of course, exit the system. We have here examples of the queuing system design. We have here a single channel, single phase system. An example is a family dentist office. We have there the arrival, the queue, and the service facility. Then, the single channel multi-phase system. Our example is a McDonald's dual window drive-thru. Then, we have the multi-channel single-phase system. We have there most banks and post office service windows. Then we have multi-channel, multi-phase system. Our example is the college registration. Performance measures are used to gain useful information about waiting line systems. These measures include the average number of customers waiting in line and in the system. The number of customers waiting in line can be interpreted in several ways. Short waiting lines can result from relatively constant customer arrivals or from the organizations having excess capacity. On the other hand, long waiting lines can result from poor server efficiency, inadequate system capacity, and/or significant surges in demand. Next, the average time customers spend waiting and the average time a customer spends in the system. Customers often link long waits to poor quality service. When long waits or long waiting times occur, one option may be to change the demand pattern. That is, the company can offer discounts or better service at less busy times of the day or week. For example, a restaurant offers early bird dinners at discount so that demand is more level. The discount moves some demand from prime time dining hours to less desired dining hours. If too much time is spent in the system, customers might perceive the competency of the service provider as poor. For example, the amount of time customers spend in line and in the system at a retail checkout counter can be a result of a new employee not yet proficient at handling the transactions. And the last one, the system utilization rate. Measuring capacity utilization shows the percentage of time the servers are busy. Management goal is to have enough servers as or to assure that waiting is within allowable limits but not too many servers as to be cost inefficient. So we calculate these measures for two different waiting line models, the single server model and the multi-server model. The easiest waiting line model involves a single server, single line, single phase system. The following assumptions are made when we model this environment. First, the customers are patient. It means that there is no balking, no reneging, nor jockeying, and come from a population that can be considered infinite. Second, customer arrivals are described by a Poisson distribution with a mean arrival rate of lambda. This means that the time between successive customer arrivals follows an exponential distribution with an average of 1 over lambda. Third, the customer service rate is described by a Poisson distribution with a mean service rate of mu. This means that the service time for one customer follows an exponential distribution with an average of 1 over mu. The waiting line priority rule used is FIFO, or the first come, first serve basis. Using those assumptions, we can calculate the operating characteristics of a waiting line system using the following formulas. First, we have their lambda, that is the mean arrival rate of customers, or the average number of customers arriving per unit of time. Then we have the mu, or the mean service rate. That is the average number of customers that can be served per unit of time. Then we have LS, or the average number of customers in the service system. Then we have WS, or the average time spent waiting in the system, including service. Then we have LQ, that is the average number of customers waiting in line. And then we have WQ, that is the average time spent waiting in line. Then we have P, or small letter P, that is or it represents the average utilization of the system. Next is PO. That is the probability of 0 units in the system. It means that the service unit is idle. Then we have PN. That is the probability that N customers are in the service system at a given time. And we have P, N is greater than K. That is the probability of more than K units in the system, where N is the number of units in the system. Please take note that the service rate must be greater than the arrival rate. That is, mu is greater than lambda. If mu is less than or equal to lambda, the waiting line would eventually grow infinitely large. Before using the formulas, check to be sure that our mu is greater than lambda. For our first example, we are given our lambda is equal to 2 cars arriving per hour, and our mu is 3 cars serviced per hour. Okay, so we need to compute for the average number of customers in the service system. Then we have there lambda over mu minus lambda. We have there 2 divided by 3 minus 2. We have 2 cars in the system on the average. Then we need to compute for the average time spent waiting in the system, including service time. So we have there Ws is equal to 1 over mu minus lambda, which is equal to 1 over 3 minus 2. We have 1 hour average waiting time in the system. Then, let us compute for LQ, or the average number of customers waiting in line. We have there lambda squared over mu times mu minus lambda. We have there 2 squared divided by 3 times 3 minus 2. We have 1.33 cars waiting in line. Then, let us compute for the average time spent waiting in line. We have there WQ is equal to lambda over mu times mu minus lambda. That is equal to 2 divided by 3 times 3 minus 2. That is equal to 2 over 3. That is 2 over 3 R, or it's also equivalent to 40 minutes. Then next is the average utilization of the system. That is lambda over mu. We have 2 over 3. That is equal to 0.667 or 66.67% of the time the mechanic is busy. Then we have the idle time of the system. We have there PO is equal to 1 minus lambda over mu, that is equal to 1 minus 2 over 3, that is equal to 0.333 or 33.33%. That is the probability that there are no cars or 0 cars in the system. Okay, so for the probability of more than k cars in the system, we can use Pn is greater than k is equal to lambda over mu raised to k plus 1. So we have here 2 over 3 raised to k plus 1. Our k is 0, 1, 2, 3, and so on. Okay, so as you can see here, if our k is 0, we have there 0.667. Okay, please take note that this is also equal to 1 minus PO. That is, the PO, of course, is the probability that our system is idle. Okay, so we have there 0.667 or the utilization or average utilization of our system. Okay, then we have here, let's say 3. Okay, so we have 0.198. It implies that there is a 19.8% chance that more than 3 cars are in the system. For the economics, the single channel economics, let's say we are given the customer's dissatisfaction and lost goodwill is equal to $10 per hour. Our WQ is equal to 2 over 3 or 40 minutes. The total arrivals is equal to 16 per day. The mechanic salary is $56 per day. The total hours customers spend waiting per day is equal to WQ times the total arrivals. That is equal to 2/3 times 16 is equal to 32 over 3 or 10.67 hours. So the customer waiting time cost is $10. Okay, that's $10 per hour times 32 over 3 or 10.67 hours. That is equal to $106.67. So for the total expected cost, we are going to add the customer waiting time cost, that is 106.67 plus the mechanic's salary per day, that is $56. So we have there the total expected cost is $162.67. Another example is the computer lab at State University has a help desk to assist students working on computer spreadsheet assignments. The students patiently form a single line in front of the desk to wait for help. Students are served based on a first-come, first-served priority rule. On average, 15 students per hour arrived at the help desk. Students' arrivals are best described using a Poisson distribution. The help desk server can help an average of 20 students per hour, with the service rate being described by an exponential distribution. Calculate the following operating characteristics of the service system. The average utilization of the help desk server, the average number of students in the system, the average number of students waiting in line, the average time a student spends in the system, and the average time a student spends waiting in line. So before we begin, the key to solving queuing problems is to identify the mean arrival rate of customers and the mean service rate. In this case, on average, 15 customers arrive each hour. On average, the consultant can serve 20 customers per hour. So once we have established these values, we can merely plug them into the appropriate formula. Okay, so we have there our lambda is 15 customers arrive per hour and mu is 20 customers per hour. First, the average utilization of the help desk server. We have there P is equal to lambda over mu, that is 15 divided by 20, that is 0.75 or 75%. Next is the average number of students in the system. We have LS is equal to lambda over mu minus lambda. We have there 15 divided by 20 minus 15 is 3. Okay. Next, the average number of students waiting in line. We have there LQ is equal to PLS. That is equal to 0.75 times 3, which is equal to 2.25 or 2.25 students. Okay. Next is the average time a student spends in the system. We have there WS is equal to 1 over mu minus lambda, which is equal to 1 over 20 minus 15. That is equal to 0.2 hours or 12 minutes. Okay, then next is the average time the student spends waiting in line. We have there WQ, which is equal to P times WS, which is 0.75 times 0.2, which is also equal to, or which is equal to 0.15 hours or 9 minutes. Next is the multi-server waiting line model. In the single-line, multi-server, single-phase model, customers form a single line and are served by the first server available. The model assumes that there are S identical servers. The service time distribution for each server is exponential, and the mean service time is 1 over mu. Using these assumptions, we can describe the operating characteristics with the following formulas. We have there S is the number of servers in the system, P that is equal to lambda over S mu, that is the average utilization of the system. We also have there PO, or the probability that no customers are in the system or the system is idle. Then we have their LQ, that is the average number of customers waiting in line. Then we have WQ, that is the average time spent waiting in line. W, that is, or WS, or W, that is the average time spent in the system, including, of course, service. Then L, or LS, that is the average number of customers in the service system. And then we are given also the probability that N customers are in the system at a given time. We are given their PO for N is less than or equal to S, and PO for N is greater than S. Okay, again, please note that the total service rate must be greater than the arrival rate. That is, S mu is greater than lambda. If S mu is less than or equal to lambda, the waiting line would eventually grow infinitely large. Before using the formulas, please check or please Be sure that our S mu is greater than our lambda. Okay, for our example, we have here, State University has decided to increase the number of computer assignments in its curriculum and is concerned about the impact on the help desk. Instead of a single person working at the help desk, the university is considering a plan to have 3 identical service providers. It expects that students will arrive at a rate of 45 per hour. According to a Poisson distribution, of course, the service rate for each of the 3 servers is 18 students per hour with exponential service times. Calculate the following operating characteristics of the service system. We have there the average utilization of the help desk, the probability that there are no students in the system, the average number of students waiting in line, the average time a student spends waiting in line, the average time a student spends in the system, and the average number of students in the system. Okay? So again, for the problem solving tip, by definition, 0 factorial is equal to 1. Okay? So for our solutions, we have there, for the first one, the average utilization, that is P is equal to lambda over S mu, that is equal to 45 divided by 3 times 18, which is equal to 0.833 or 83.3%. Next is the probability that there are no students in the system. Okay, so we have there P sub O is equal to 45 over 18 raised to 0 over 0 factorial plus 45 over 18 raised to 1 over 1 factorial. Then 45 over 18 raised to 2 over 2 factorial plus we have there 45 over 18 raised to 3 over 3 factorial times 1 over 1 minus 0.833 raised to negative 1. We have there 0.045 or 4.5%. Okay, so that is 4.5%. That's the probability of having no students in the system. Next, the average number of students waiting in line. We have there LQ is equal to 0.045 times 45 over 18 raised to 3 times 0.833 over 3 factorial times 1 minus 0.833 squared. That is equal to 3.5 students. Okay? Then the average time a student spends waiting in line, we have there WQ is equal to LQ over lambda, which is 3.5 over 45. That is 0.078 R or equivalent to 4.68 minutes. Then, the average time a student spends in the system, that's WS, or W is equal to WQ plus 1 over mu. We have there W is 0.078 plus 1 over 18, which is 0.134 R or 4.68 minutes. Then the average number of students in the system, we have L is equal to lambda times W, which is equal to 45 times 0.134 or that's equal to 6.03 students. Okay, next is the undefined and constant service times. Sometimes it cannot be assumed that a waiting line system has an arrival rate that is Poisson distributed or service times that are exponentially distributed. For example, many manufacturing operations use automated equipment or robots that have constant service times. Thus, the single server model with Poisson arrivals and constant service times is a queuing variation that is of particular interest to manufacturing operations. Constant service times occur with machinery and automated equipment. Constant service times are a special case of a single server model with undefined service times. The constant service time model is actually a special case of a more general variation with a single server model, in which service times cannot be assumed to be exponentially distributed. As such, service times are said to be general or undefined. The basic queuing formulas for the operating characteristics of the undefined service time model are as follows. The key formula for undefined service times is for the LQ, the number of customers in the waiting line. In this formula, mu and s are the mean and standard deviation, respectively, for any general probability distribution with independent service times. For the Poisson distribution, the mean is equal to the variance. This same relationship is true for Poisson service rates if service times are exponentially distributed. Thus, if we let S is equal to mu in the preceding formula for LQ for undefined service times, it becomes the same as our basic formula with exponential service times. In fact, all the queuing formulas become the same as in the basic single server model. As an example of the single server model with undefined service times, consider a business firm with a single fax machine. Employees arrive randomly to use the fax machine at an average rate of 20 per hour. According to a Poisson distribution, the time an employee spends using the machine is not defined by any probability distribution, but has a mean of 2 minutes and a standard deviation of 4 minutes. The operating characteristics for this system are computed as follows. We have there PO, we have 1 minus lambda over mu is 1 minus 20 over 30, that is equal to 0.33, the probability that no one is using the machine. LQ, that is lambda squared times the standard deviation squared, or the variance, plus lambda over mu squared over 2 times 1 minus lambda over mu is equal to 20 squared times 1 over 15 squared plus 20 over 30 squared over 2 times 1 minus 20 over 30, which is equal to 33 or 3.33 employees waiting in line. For the LS or L, that is equal to LQ plus lambda over mu, which is equal to 3.33 plus 20 over 30, that is equal to 4 employees in line and using the machine. WQ is equal to LQ over lambda, that is equal to 3.33 over 20, that is equal to 0.1665 R, or 10 minutes waiting in line. W or WS is equal to WQ plus 1 over mu, which is equal to 0.1665 plus 1 over 30, that is equal to 0.1998 R, or 12 minutes in the system. U, or we can also call it P, or small letter P, that is equal to lambda over mu, that is equal to 20 over 30, that is equal to 0.67 or 67%. That is for the machine utilization. In the constant service time model, there is no variability in service time, so S is equal to 0. In the case of constant service times, there is no variability in service times. Thus, S is equal to 0. Then we can substitute S is equal to 0 into the undefined service time formula for LQ. And the results in the following formula for LQ with constant service times is LQ is equal to lambda squared over 2 times mu minus lambda. And of course, WQ is just the same. That is equal to LQ over lambda. Okay? So, the following example illustrates the single server model with constant service times. The Petroco service station has an automatic car wash, and motorists purchasing gas at the station received a discounted car wash depending on the number of gallons of gas they buy. The car wash can accommodate one car at a time, and it requires a constant time of 4.5 minutes for a wash. Cars arrive at the car wash at an average rate of 10 per hour. Of course, that's Poisson distributed. The service station manager wants to determine the average length of the waiting line and the average waiting time at the car wash. Okay? So, first is let us determine lambda and mu such that they are expressed as rates. We have their lambda is equal to 10 cars per hour. Mu is equal to 60 divided by 4.5, that is equal to 13.3 cars per hour. Okay, so substituting these values into the queuing formulas for the constant service times, we have their LQ is equal to 10 squared over 2 times 13.3 times 13.3 minus 10, which is equal to 1.14 cars waiting. Okay, next for WQ, we have there 1.14 over 10, which is equal to 0.114 hour or 6.84 minutes waiting in line. After calculating the operating characteristics for a waiting line system, sometimes you need to change the system to alter its performance. Let's look at the type of changes you can make to the different elements of the waiting line system. First, customer arrival rates. You can try to change arrival rates in a number of ways. For example, you can provide discounts or run special promotions during the non-peak hours to attract customers. Second is the number and type of service facilities. You can either increase or decrease the number of server facilities. For example, a grocery store can easily change the number of cashiers open for business. The store increases the number of cashiers open when lines are too long. Another approach is to dedicate specific servers for specific transactions. One example would be to limit the number of items that can be processed at a particular cashier, or to limit a cashier to cash-only transactions. Still, another possibility is to install self-service checkout systems. Third is changing the number of phases. You can use a multi-phase system where servers specialize in a portion of the total service rather than needing to know the entire service provided. Since a server has fewer tasks to learn, the individual server proficiency should improve. This goes back to the concept of division of labor. Next is server efficiency. You can improve server efficiency through process improvements or dedication of additional resources. For example, a cashier accuracy and speed are improved through the use of scanners. Service speed can also be increased by dedicating additional resources. For example, if a grocery bagger is added at each cashier station, service speed will be improved and customers will flow through the system more quickly. Next is changing the priority rule. The priority rule determines who should be served next. There are priority rules other than first come, first served. If you want to change priority rules, consider the impact on those customers who will wait longer. Then, changing the number of lines. Changing to a single line model from a multi-line model is most appropriate when the company is concerned about fairness for its customers. A single line ensures that customers do not jockey in an attempt to gain an advantage over another customer. Multi-line models easily accommodate specialty servers. Once these changes are suggested, evaluate their impact on the performance characteristics of the waiting line system. Changes in one area can require changes in other areas. For example, if you achieved a more constant customer arrival rate, you may be able to reduce the number of service facilities. Although it is unlikely that you calculate performance measures for the lines you wait in on a day-to-day basis, you should now be aware of the potential for mathematical analysis of these systems. More importantly, management has a tool by which it can evaluate system performance and make decisions as to how to improve the performance while weighing performance against the cost to achieve that performance. Waiting line models are important to a company because they directly affect customer service perception and the costs of providing a service. Several functional areas are affected by waiting line decisions. Like, for example, in accounting, it is concerned with the cost of the waiting line system used. If system average utilization is low, that suggests the waiting line design is inefficient and too expensive. Poor system design can result in overstaffing or unnecessary capital acquisitions in an effort to improve customer service. In marketing, it is concerned about the response time for customers, how long customers must wait in line before being served, and how long it takes to be served. Quick service or response can be a competitive advantage. Long waits suggest a lack of concern by the organization or can be linked to a perception of poor service quality. Purchasing must be sure to buy capital equipment capable of achieving the proposed service rate. Operations uses waiting line theory to estimate queues or waiting times at different processing points to allow for a better estimate of lead time and improve due date delivery. Promising. Operations is also affected by the system design. When single-phase systems are used, operators must have greater skills. The organization needs to hire employees with higher skill levels or provide training to upgrade the workforce. Okay, so for the formula review, these are our formulas for the single server waiting line models and for the multi-server waiting line models.